In this video, we'll be talking about transformations. Specifically, we'll be transforming a quadratic relation. We will spend a whole unit on transformations in grade 11, so it's pretty important that we learn it properly the first time around, so when we study this in grade 11, it'll be easy peasy lemon squeezy. Before I talk about transformations, I actually want to review an idea that we talked about when we introduced quadratic relations, which is there are three different ways to express the equation of a quadratic relation. We can talk about the equation standard form, in vertex form, or in factored form. Okay, so once again, I can give you the equation standard form, vertex form, or in factored form. Now, I asked this question in the first lesson, in the first video when I introduced quadratic relations, and that was, why do we have three different ways of expressing the same idea? Okay, even though these equations, they clearly look different, okay, but they really represent the same quadratic relation. Okay, so I can express it in standard form, vertex form, or factor form. Now, why would I do that? Because each different form gives us new information about the quadratic relation. Okay, so when I express it in factor form, I know something. I don't want to give it away, but I know something about the quadratic relation. If I express in vertex form, I know something else. And if I express in standard form, I also know something else about the quadratic relation. So each form is useful in a way. I would argue one is more useful than the other, but each does give me new insight, new information. Okay, so in this chapter, we will pretty much spend all our time in vertex form, okay? I would argue that vertex form is the one that gives us the most useful information about the quadratic relation. So that's probably why we start with vertex form. It's the easiest to work with, especially when it comes to transformations. We want to express it in vertex form. So let's take a look. The vertex form, what does it give us? Well, surprisingly, it gives us the vertex of the parabola. So it's not a coincidence that the two letters we chose here for our constants or for our parameters are h and k. Okay, h and k. What did we see h and k earlier? Yes, h and k were the letters we chose for the vertex, right? So hk actually represents the vertex of the parabola. And if hk is the vertex of the parabola, then guess what? The axis of symmetry is x equals h. And when you are given the equation in vertex form, you also know the transformations applied to y equals x squared to obtain your new parabola or your new quadratic relation. Now, we will talk about transformations in a second, but hopefully from the first 2 points you realize that the vertex form of the quadratic relation is very, very nice. It gives us the vertex and it gives us the axis of symmetry. That's very, very powerful, especially if you think about graphing the parabola. The vertex is probably the most important point when it comes to graphing the parabola. Okay, so enough said, let's talk about transformations. So what are transformations? A transformation is a change made to a figure or relation such that the figure or the graph of the relation is shifted or changed shape. Okay, so basically every manipulation that we make is called a transformation. Now we are specifically going to talk about translations, reflections, stretches, and compressions. Okay, so these are all different types of transformations. And by the way, I realize in elementary school, they spend a lot of time on transformation. So this is actually something I find students are pretty good at. Okay, so a translation is when you shift the figure. Okay, so the shape doesn't change, you're just shifting it. Imagine you have like a shape well, hopefully you can imagine your parabola. You're just sliding it around. So you can slide it left or right, up or down. So when you slide it around, the shape of the parabola does not change. What about a reflection? Okay, imagine if you have a parabola and you reflect it across the the x-axis. Okay, if you reflect it across the x-axis, how does the parabola look? And then we also have these stretches and compressions. Now, what we are going to do is we're going to stretch it vertically. Okay, we're going to apply a vertical stretch, because if you think about it, you can actually stretch it horizontally, but that's in grade 11 actually. So specifically vertical stretches and vertical compressions. So if you're stretching it vertically, hopefully you can imagine your parabola is going to be narrower. And if you vertically compress it, your parabola will look a little wider. All right, so just keep those in mind, okay? Translations, reflections, stretches, and compressions. Those are the key words I'm going to use over and over again when it comes to transformations. So I have an animation to help you study transformations, and then we'll come back and fill in the rest of this handout once we finish studying the animation. That we are going to use to explain transformations. Let's first start off by looking at the equation here. So we have y equals a times x minus h all squared plus k. So of course, this is the equation in vertex form. And what we can do is actually use a computer to change the values of a, h, and k. We can change it all at once, or we can change them one at a time. So what we're going to do is we're going to change them one at a time, and then we're going to change them all at once. And I want you to take a look at this beautiful blue parabola here. This is our original parabola. Okay, this is the original y equals x squared parabola. We call this the original parabola because it's the simplest one graphically and algebraically. Okay, the equation is y equals x squared. To be honest with you, I can't think of a quadratic equation that's simpler than y equals x squared. Okay, and graphically it's really pretty. Okay, it's centered. I mean, its vertex is at the origin. It's opening up. So everything about this is very nice to work with. So this is our original parabola, and every other parabola we have is created by this original parabola of y equals x squared. And we're going to create these other parabolas by applying the transformations. So whether it's a translation, a vertical stretch, vertical compression, or reflection, that's how we're going to create these other parabolas. Okay, so without any further ado, let's change k. Interesting. Oh, okay. So hopefully you see that k is translating the parabola up and down. So the red one is y equals x squared. Okay, that's our original parabola. So for example, if k is 1, you shifted the red parabola 1 unit upwards. If it was 2, it's 2 units up. If it was 3, 3 units up. Negative 1, ooh, 1 unit down. 2 units down. Okay? So k is basically introducing a vertical translation. What about h? Ooh, H is very nice. It's introducing a horizontal translation. So if you have a negative value for H, we are translating to the left. And if H is positive, we're translating to the right. Perfect. Nice. Okay. So if it's 1, 1 to the right, 2 to the right, 3 to the right, 1 to the left, 1 to the right, 2 to the left, and 3 to the left. Okay. All right, last one here. A. I'm going to just show this one, and I'll let you just take a look at it and try to make sense of it yourself. Beautiful. Nice. I'm going to let it come back. And there we go. Okay. a to be equal to 2. And what we have here is that hopefully you can see that the blue parabola is skinnier than that of the red parabola. Okay, so the blue parabola is skinnier than the red parabola. And we want to ask ourselves, why is the blue parabola skinnier than the red parabola when a is equal to 2? Because when a is equal to 2, what that means is that we are going to double the distance from the point to the red parabola, the points on the red parabola to the x-axis, we are going to double that vertical distance. Okay, so from this point to the x-axis is 1 unit. Guess what? We've doubled that distance, so now it becomes 2 units, and that's how we get the points on the blue parabola. Like over here, if I'm at this point, the vertical distance from this point to the x-axis is 4. So guess what? We double the distance, and now it's 8 units. Whenever, so if you double all these vertical distances, what you're going to get is a parabola that is skinnier. Okay. What if we let a equal 3? Ooh, the vertical distance is now 3 times of that as before. Okay. So now it's like a vertical distance of 1 is now a vertical distance of 3. What if a is 4? Now the distance is quadrupled, right? It's 4 times of that of before. Now wait a minute. How can we make a vertical compression? Is it possible to make this distance lesser than that of before? Can we make this point closer to the x-axis? Oh yes, we can. If a was half, right? Look, now the distance is not larger than that of before. It's actually half of that of before. So it's closer to the y-axis. And if all the points are closer to the y-axis, because it's half of that of before, then now what you see is a parabola that is wider. Okay, so this is called a vertical compression. What if it was 0.25? Whoa, the vertical distance is now a quarter of that of before. If it was 0.1, whoa, even wider. Okay, so you can of course make it wider and wider and wider. And the last transformation that I want to talk about is what we have here. This is a reflection across the x-axis. Okay, if you can imagine, you can use the x-axis here to create your mirror image. So we've taken this red parabola, our original y equals x squared parabola, and reflected it across the x-axis. And that's how you get this new parabola. So that's it. We talked about stretches, vertical stretch, vertical compression, reflection, horizontal translations, and vertical translations. Okay, simultaneously, and see what happens. So hopefully you can see that when we animate all of them together at the same time, you can really create any parabola you want by transforming the original y equals x squared parabola. Apply the correct stretch or vertical stretch or vertical compression, reflection, translation, and you will be able to get any parabola you want. Okay, so it's really helpful to think that every parabola is created by transforming the original parabola. Okay, so let's go back to the handout. Okay, so hopefully you appreciated the animation. Let's go back to the handout and fill in the rest of the cells here, or fill out this table. So we are going to summarize what we saw in the animation just before we forget. So if a is greater than 1, what we have is a vertical stretch. Okay, hopefully you remember when, like for example, if a was 2, the vertical distance from the point to the x-axis doubles. So what you see is a narrower parabola. We say that's a vertical stretch because the vertical distance is increased. So we say vertical stretch by a factor of a. Now, why is it a factor? Because we were saying it was multiplied. It was multiplied by, I don't know, let's say 2 or 3 or 4. So that's why you use the words factor. When a was between 0 and 1, this distance, this vertical distance between the points in the y-axis, they did not increase. In fact, they decreased. So this time, you don't see a vertical stretch, you see a vertical compression by a factor of 1 over a. The textbook does it a little differently. We are going to go through an in-depth explanation why I would write it as 1 over a and why the textbook says a. But we'll save that for another time. As long as the key idea though is you understand what a vertical compression is, okay? When a is less than 0, what you see is a reflection across the x-axis. Reflection, I like to say with respect to x-axis. When h is less than 0, we have a horizontal translation left, to the left. And if h is greater than 0, we say horizontal translation to the right. So these are all, you can go back to the animation and look at it again. That's what we gathered from the animation. Now we will definitely explain what we see from the animation algebraically, but for now I want to summarize those ideas before we forget. If k is less than 0, there's a vertical translation down, downwards, down. Or, if k is greater than 0, is a vertical translation up or upwards. Okay. What we're going to do now is we're going to take a look at some equations, and then we are going to state the transformations. And one important note, when you state the transformations, you always state translations last. And we will explain that in the next lesson as well. So the next lesson is really important. We're going to explain what we see through the animation using algebra, and we'll also try to explain why we apply translations last. So whenever you state them, as long as you state the translations at the very end, we will be good. You can do stretches and compressions first or reflections first. It's up to you. Okay, so a vertex form, beautiful. A is equal to 2, h is equal to 3, and k is equal to 3. Okay, be very careful here. H is 3. I know it's very tempting to write negative 3 here, but if you look at the original form of the vertex form, it's y equals a times x minus h all squared plus k, right? It's x minus h. So since you see x minus 3, h is actually positive 3, okay? It's not negative 3. Okay, so if a is 2, we have a vertical stretch by a factor of 2. If h is 3, we have a horizontal translation 3 units right, because h is greater than h is positive, so as you're going to the right. Vertical translation 3 units up, right? Because k is positive. Okay, here, once again, I'm going to state my parameters. A is half, h is 3, and k is 0. Okay, So this is going to be vertical compression by a factor of 2. Because your vertical distances from the points to the x-axis, they are half of that of before. So if it's half of that of before, then you say vertical compression by a factor of 2. You took the previous distances, the vertical distances, and you divided them by 2. So it makes sense when you write the words compression by a factor of 2. Horizontal translation, H is positive, so horizontal translation 3 units right. Alright, let's keep going. A is 4/3. H, you can write x minus 0 all squared if you're really uncomfortable. If you really can't see why h is 0. Okay, it's clear. X squared is x minus 0 squared, of course. I mean, silly to write it like that, but a lot of students really struggle seeing why h is equal to 0 here. So h is 0 and k is negative 15. Okay, so a is greater than 1, so vertical stretch by a factor of 4/3. Vertical translation 15 units down. Okay, this one is actually pretty easy. A is 1, H is 1, K is 0. There's only one thing happening. Horizontal translation 1 unit right. Ooh, this one, trick question. I can't tell you. I don't know. Because it's not in vertex form. Okay, so later on we can answer this question. Not right now because we don't have the ability to go from standard form to vertex form. Since that's the case, then I can't tell you the transformations. Okay, so that's one of the benefits to having your equation in vertex form. You can establish what the transformations are. So remember, that's one of the key ideas I really want to emphasize. Each form is useful in its own way, and vertex form is really good in the sense of giving you what the transformations are. That's one of its benefits. Okay, let's see. So this time they're going to give me the transformations, and then I have to come up with the equation. So vertical stretch by a factor of 3 and a reflection on the x-axis. So A is not only is it 3, it's going to be negative 3. 3 units down, so that means no horizontal translation, and K is negative 3. So the equation will look something like that. Vertical compression by a factor of 4, horizontal translation 8 units left, vertical translation 2 units up. So let's see. A is going to be 1/4, okay? Because if I divided the distance by 4, the vertical distance, that means I must have multiplied by 1/4. Dividing by 4 is exactly the same as multiplying by a quarter. H is negative 8, okay, because I went 8 to the left. K is 2. Let's put this all together. 1/4 x. Now be careful, it's x minus h. So if it's negative 8, right, it's going x minus negative 8, which is plus 8. Okay, last one here. A is negative 8/7 because there's a vertical stretch by a factor of 8/7 and a reflection on the x-axis. H is 2/3. It's going to the right, so it's positive. And K is negative 3/4 because I went 3/4 units down. So y equals negative 8/7, x minus 2/3, Okay, always remember the original form is x minus h. That always throws students off. Oops, and k is negative. Later on, we are going to explain why it's negative here, okay? Because a lot of students really want to change a positive, but you're just not allowed to. The original form of vertex form is x minus h all squared. Okay, so we basically in this video, we saw the animation, we concluded the ideas from the animation, but we didn't really explain the ideas very well. We didn't explain why is there vertical stretch, why is it, like for example, why did the distance double vertically? Why did they get halved? Why am I going to the right? Why am I going left? Why am I going? So we are going to answer all those questions, but at the very least, just by using the animation, you can state the transformations. And if I give you the transformations, you can come up with the equation. Okay, we just get a good feel for transformations in this lesson. In the next lesson will be a lot more algebra involved, and hopefully you can explain what you see using your number sense.